Good afternoon, everyone. I am Ed Albin, Department Chair for Space Studies at the American Public University System, and we'd like to welcome you to our session this afternoon. This is part one of two sessions, and the session this afternoon that will run until 2:15 p.m. today is entitled Space, Human Factors, and Life Support Technology for Space Exploration. And we have three distinguished speakers that I'd like to introduce before we get underway. We have Dr. Kristen Miller, who is an associate professor of space studies for American Public University. And Kristen will be talking about our analog research group, which has analog missions in North Dakota and Utah. Her official title for the presentation is Destinations in Space, I should say. And a little later today, she'll be talking about those. I sort of jumped ahead. Our next speaker is Dr. J.D. Polk with NASA, and he is the Chief Health and Medical Officer for the Astronaut Corps at NASA, which is pretty cool. And the title of his presentation today is NASA's Spaceflight Human Standards for Exploration Class Missions. Really exciting stuff. And finally, we also have from NASA, Vincent Michaud, if I'm pronouncing that correctly, who works with JD and is the Deputy Chief Medical and Health Officer for NASA. And his presentation is U.S. Space Force Human Support and Life Support Technology. So once again, welcome to our CISA session, Space, Human Factors, and Life Support Technology for Exploration. And we'll kick off with Dr. Miller, who will tell us about destinations in space.
Thank you so much. So I'm going to go ahead and share my screen here. Just while I'm pulling it up. So in this talk, I'm going to focus on, as Dr. Albin said, destinations in the solar system. And later today, we'll have a panel on analog research. So I hope you'll all come to that as well. But the reason we're starting with destinations is because before we can successfully navigate the challenges of human spaceflight, we need a solid understanding of the risks and resources of each unique environment. And these topics are part of the new APUS Space Human Factors concentration. And these are, I just want to share some of the learning objectives from that concentration that will be launching in maybe 2025 here. So the advantages of human space exploration. There are many reasons why we value human space exploration and why we pursue it in spite of the difficulties. And one is because as amazing and successful as the rovers and orbiters and flyby missions have been, they can't quite match the benefits of having actual people in the environment to study both the environment and the materials. Human spaceflight enables us to utilize materials, for example, in space mining, and enables us to utilize the environment. For example, there are applications in medicine and manufacturing that benefit from the microgravity environment. Human spaceflight is exciting. It inspires the public and increases public support for missions, and it also provides the potential to establish an off-world presence for humanity. However, the space environment is not conducive or supportive of life in any way, and it's becoming clear that the use of Earth resources in off-world settlements is not sustainable. This is due to the high cost, high resource and energy requirements, the time needed to plan and execute launches, as well as the time and travel. For the moon, there's some possibility that this this can support, but for any other destination, it's just not feasible, which means that as we look outward in the solar system, we need to be aware and be developing bioregenerative life support systems and in situ resource utilization. So today what I'm going to do is talk about some of the environments, some of the destinations, and some of the resources we can use there, and some of the unique challenges to each of them. Starting, of course, with our favorite destination, the moon, which is exciting because NASA's well on their way to returning through the Artemis mission. So the lunar environment is a hard vacuum. It's 10 to the negative 15th atmospheres, barely any atmospheric pressure at all. The gravity is about 1/6 that of the Earth, which is better for the human body than microgravity, but still a challenge. It's still definitely not what we're used to here on Earth and not what our bodies are designed to tolerate. Lower gravity means that fluid movements are different than on Earth. This can affect plant physiology and plant growth. So there's a challenge for growing botany on the moon. The lower gravity has also contributed to the lack of atmosphere on the moon. Lighter gases, the moon wasn't able to hold on to them, they escaped, and other gases have been stripped off by exposure to the solar wind. The lack of atmosphere means that there's no thermal insulation and no pressure on the lunar surface. And one of the consequences of this is that even micrometeoroids are not slowed before they hit the surface. In fact, that's one of the main forms of erosion on the moon. And this can lead to pitting of materials, fractures in materials that are already strained. One mitigation is to utilize coatings of composite materials, which can protect against, for example, 1 microgram meteoroids, and there's a near constant rain of them on the lunar surface, but structures will definitely need to be protected from larger impacts, which are a little bit less common, but still frequent on the lunar surface. Now, the moon's rotation is tidally locked to the Earth in a 1-to-1 synchronization, which is why we have a near side and a far side of the moon. Its axial tilt is very slight. It's only about 6 degrees, which means that there's not really a seasonal climatic variation on the moon, but there is a strong day-night variation. The albedo of the surface rocks on average on the moon is about 0.1. And for reference, that's pretty close to the albedo of black paint. So these materials are quite absorptive. And that leads to some pretty big temperature swings. For example, in the daytime at the equator, we can get temperatures as high as 400 Kelvin, whereas at nighttime in the poles, the temperature is going to be as low as 200 Kelvin. And one of the exceptions to these swings are the shadowed recesses of craters near the poles, which are in near constant shadow or even constant shadow. And in those areas, you can see that there is really no day-night variation. The temperatures are extremely low at 40 Kelvin, but we don't have those temperature variations, so that is that's something that can help. The day-night cycle on the surface of the moon is long. It's about 14 to 15 days for day and for the night periods. Which means that during the day, we have a prolonged period of time when we have access to solar energy for reliable power. We also need to mitigate that long night period. The situation is a little bit better in terms of power at the poles. The sun's elevation is only about 1.5 degrees above or below the horizon. And that means that the rims of some craters are in near constant illumination. And so that can provide a very reliable and constant energy source. These features of the moon cause a lot of challenges for materials and for machineries and for technology. One of the issues is thermal shock, which occurs when different parts of an object expand thermally at different rates due to rapid temperature variations, such as we find between day-night cycles on the moon. This can lead to failure-inducing strains. It affects materials such as glass, ceramics, metals that are below the glass transition temperature. And it can lead to thermal strain and thermal fatigue. Another issue is the concept of thermal control on Earth. There are a lot of systems that require thermal control, and we typically mitigate that with convective heat transport, which simply isn't going to work on the moon. So we need to find other ways of maintaining the thermal equilibrium. under the very low temperatures that we find on the moon, many materials will become brittle, they'll lose ductility. One mitigation for this is to develop better materials that can withstand the low temperatures, that can withstand the temperature variations. One that I find interesting is NASA's developing a bulk metallic glass gears like the one that's pictured here, and these can function in extreme cold without heating, so it saves a lot of energy. And there are many companies working on some solutions and different materials that might make it easier to live and work on the moon. Radiation exposure is a big issue in the lunar environment. Without a magnetic field and without an atmosphere, then there is no protection from the radiation that's coming in from both the sun and from outer space. Electromagnetic radiation from the sun, the average lunar energy density is the same as that on Earth, 1360 watts per meter squared. The sun is a source of ionizing radiation, UV, X-ray, and gamma ray radiation from the sun. This radiation can degrade plastics. It can degrade the composite materials like the ones that might protect us against micrometeoroids. So that's a challenge with that. The moon is also subject to a flux of particle radiation. And I list all the different sources of particle radiation, the kinds of particle radiation here. High energy charged particles are also ionizing. So this is another source of ionizing radiation. Ionizing radiation, as we said, it comes from the sun, it comes from the solar wind, it comes from solar particle events, and it comes from galactic cosmic radiation, and it definitely requires shielding. So the higher the energy, the thicker the shielding is needed. We don't have really good ways of shielding in particular from galactic cosmic radiation, although many people are working on developing some good shielding options. But it's clear that a spacesuit is not adequate shielding for large solar particle events, which means that we need to be very careful about this during, for example, EVAs, and in habitats, we would need some safe rooms with additional shielding options to protect from this radiation. The radiation can cause a considerable amount of damage to, for example, solar panels, organic material, including people, circuits and electronics. It can also interrupt communications. Now, the moon doesn't have soil. It has what we call regolith, which lacks, the difference is that regolith lacks living matter, and it is very similar to the underlying parent rock. So there's no associated organic matter or microbiome in the lunar regolith. It's sterile and nutrient poor. It's particularly lacking macronutrients such as nitrogen, phosphorus, sulfur, which is a challenge for plant growth. It's highly alkaline, highly abrasive. There's low cohesion of mineral components. It has a low water holding capacity. That's also a challenge for plants. And it has some toxicity, so it can affect the lungs and respiratory systems. One interesting property of the regolith, interesting and challenging, is that it has a very low electrical conductivity. So this means it retains electrostatic charge. So it sticks to surfaces. It's very hard to just brush off. Surface electric fields on the moon enhance this effect and drive dust transport. But this adherence causes some difficulties. It can limit visibility on landings. It can stick to spacesuits, it can stick to materials. It has both mechanical adhesion due to the barbed shapes of the dust and also electrostatic adhesion. And it causes, when things are coated with the dust, then you can get thermal effects and health risks. There's breathing difficulty, chronic respiratory problems. The regolith grains themselves are coated with highly reactive chemical bonds, which can exist because of the near vacuum environment of the moon, and these are toxic. The conductivity of the regolith does vary. It depends on surface temperature as well as IR or UV radiation. So it's not a static quantity. As we said, the moon is lacking in a magnetic field, so shielding is required. There is in situ water at the poles of the moon, and that's very effective for shielding from solar particle events, for example. Any material that contain hydrogen, like polyethylene, would be a potential here. And actually, the regolith has the potential to be used for shielding. We would need about 2 to 5 meters depth of regolith to provide effective shielding, but this might be a possibility, for example, covering habitats, which would limit radiation exposure maybe only to EVAs or to certain activities on the surface, which would has a potential to greatly decrease the net exposure of a human working on the surface of the moon. The polar regions, as we said, they're of special interest because the polar regions, we found stores of water, which can provide shielding, fuel, and life support. There are also areas of near solar illumination, so there's reliable power. And that's one of the reasons that we are looking at returning to the poles of the moon. So that's a brief little introduction to the moon. We're going to look at Mars now. Mars is another potential and interesting destination, and probably our next step after the moon. So Mars has many of the same challenges that the moon has, but it also has some unique features. The gravity is a little bit more than the moon, still less than that of Earth, about 1/3 that of Earth, but better, easier for the human body to tolerate than microgravity and better than the moon. The atmospheric pressure on Mars is less than 1% that of Earth. It's about 0.006 atmospheres. This is pretty small compared to Earth, but it's still significantly higher, many orders of magnitude higher than the moon. There's enough atmosphere that drone flight is possible. For example, we've seen the success of Ingenuity pictured here. It also means that heat shields are required for descent. The atmosphere is about 95% carbon dioxide. It provides little to no protection from cosmic rays and no temperature moderation through a greenhouse effect. It's just simply not dense enough for that. Mars has a tilt very similar to an axial tilt, very similar to the tilt of Earth. So there are seasonal variations on Mars, just as there are on Earth. It has 4 spring, summer, winter, and fall seasons. The average temperatures are much colder, but the average temperature is around 200 Kelvin. The equator has a variation between 293, about 300 Kelvin and 100 Kelvin. That's during the summer. That would be a day-night variation. The polar low gets down to about 120 Kelvin in the winter. For mid-latitudes, we've got about a 60-degree variation between night and day, which is about 3 times stronger than the variations that we see on Earth, but less than the variations that we're seeing on the moon. So we still have temperature swings, but they are a little bit easier to deal with. Mars does not have a magnetic field currently. InSight has measured a field of about 2 microtesla on the surface of Mars, which is about 10 times less than the Earth. But there's no global magnetic field. The core is not creating a magnetic field dynamically the way that the Earth does. What we've found is a field that is a fossil magnetic field that's been embedded in the rocks. And it does not provide significant radiation protection on the surface, so shielding will be needed on Mars as well. One thing that's really interesting about Mars, and one of the reasons that we're intrigued with it, is that there are water sources on Mars. So we find water in permafrost, in polar caps, deep subsurface ice deposits. There's a small amount of water vapor in the atmosphere, and ample evidence of wet conditions in Mars's past, which makes it a really intriguing place to study. For example, the outflow channel that's pictured here, there are also gullies and canyons, a lot of ample evidence of how different Mars was in the past. There are clouds on Mars. They're mostly ice particles. And there are, of course, the Martian dust storms, which have very high velocities but very low densities. So they are not going to blow over your spacecraft like in the Martian, but they can coat material with dust, which can be an issue. The Martian regolith is similar to lunar regolith in that it is not very conducive to plant growth. It contains, in addition to the properties of the lunar regolith, it contains perchlorates in levels which are toxic for plants. So this is a challenge for plant growth. It leads to reduced growth. The issue with perchlorates is that they can lead to increased metal and phosphate levels in the regolith. So even if you remove the perchlorates, the regolith remains toxic to plants, and mitigation is needed for materials or microbes of some kind to absorb these metals out of the regolith in order to be able to grow plants and for consumption, for human consumption. Martian regolith is prone to cementation and crusting, which prevents plant growth by limiting water infiltration and root penetration. This can be alleviated by creating mixtures of regolith and organic material, and there are a lot of different groups which are studying different mixtures and how these can be used to use regolith as a growth medium. Great. So looking at other places in the solar system that might be interesting to visit, there's our nearest neighbor, Venus. Venus, of course, is pretty uninhabitable on the surface where the temperatures are extreme and pressures are extreme. But if we look at the atmosphere of Venus, there are actually levels where it might be possible to think about for example, a floating scientific workstation of some kind or observation station. If we look at about 50 kilometers above the surface of Mars, the pressure there is about 1 atmosphere or 1 bar, which is pretty almost identical to Earth. Venus has abundant solar energy. Temperatures at this level actually will support liquid water. The gravity is about 90% that of Earth, so there aren't any of the gravitational or the microgravity issues that we get on other worlds. And the atmosphere contains some resources that are really useful, such as carbon, oxygen, hydrogen, nitrogen, and sulfur, which could potentially be taken from the atmosphere and used within the habitat. The atmosphere also contains droplets of sulfuric acid, but we do have pretty well-developed techniques for dealing with acid corrosion, so we can mitigate that. One thing that's in our favor is that breathable air is a lifting gas. It'll support about 0.5 kilogram per cubic meter, so that helps in providing some lift for habitat. The thick atmosphere of Venus provides 1 kilogram per square centimeter of mass shielding from radiation. So that is some built-in radiation protection, which again is very useful. So this might, well, it may not be a place to, live as a community. It's definitely an interesting possibility for a science observation station. Another location in the solar system that we're interested in and that we'd like to explore more, of course, would be Titan, Saturn's moon, which in many ways is sort of like a colder version of Earth, although it does have some different properties. Titan has an almost Earth-like atmospheric pressure. It's about 1.5 atmospheres on the surface, so compared to 1 atmosphere on the Earth. So this is about the pressure that you would get about 15 meters underwater. It is, of course, extremely cold due to its position in the solar system, and while it has a substantial atmosphere, it is not breathable. However, one thing that is really useful about Titan is that it has easily abundant energy sources, easily accessible, abundant energy sources. There's lots of methane. There's a possibility of hydropower from tides, for example, which have been found in maybe in the throat of Kraken. Wind turbines in the upper atmosphere are a possible energy source, and maybe solar arrays. Titan's distance from the sun, they'd have to be pretty big, probably about the size of like the US, but they'd also need constant cleaning, but it's not out of the question. It's a possibility. So there are lots of energy resources and lots of interesting terrain, absolutely. And finally, I just want to touch briefly on the icy moons of the solar system, which are places we would love to explore in more detail. These are the moons of Jupiter and Saturn, ocean worlds, and one thing that makes them incredibly interesting is the presence of subsurface liquid water oceans. We've also detected molecular hydrogen in the plumes, which is a source of free energy for microbes that can combine it with carbon dioxide. The potential for finding some sort of microbial life under the surface exists on these planets, and they're exciting places we'd love to explore more. I think my time is about up, so I will just say that NASA's rovers and orbiters and flyby missions have given us a solid understanding of the challenges in each of these potential solar system destinations, as well as vital information regarding the unique resources that are available to aid in manned space exploration. And this is our challenge as we move into the future. And I will stop there. Yeah.
Right. Well, thank you very much for that fascinating overview, Kristen. Vincent and JD and I, and also Arnold, have tried to field some questions, many questions in the chat, and I think we have done a pretty good job there. And we'll pause for a moment to see if there are any other specific questions for you. If folks want to pop those into the chat, Kristen can field those. And otherwise, we'll transition over to our next speaker, JD Polk, who will tell us about NASA's spaceflight human standards for exploration class missions. Thank you.
Thanks, Ed. Let me know if those slides are showing up.
Looks good.
Great. Well, as we talk about standards for space medicine, as Dr. Miller mentioned, first thing that you have to start to look at is what is your design reference mission? And a design reference mission, or DRM as we call it at NASA, is where are you going? And what do you expect to do there? Are you going to just land? Are you going to orbit? Are you going to have rovers? And the vehicles all change, and the standards and requirements for those vehicles all change depending on the design reference mission. So if you think of Virgin Galactic on the left, they're just going up into suborbital space and coming down. Not going to have exercise equipment on it, for example. Not going to have a lot of the other things that you see on the International Space Station. Same with Blue Origin, simply going up and down into suborbital and coming down, versus Boeing on the right, which is an orbital flight. It's going to take them a little longer to get to the space station. The heat shield has to be more robust for that vehicle, because orbital flight, you obtain a velocity of 17,500 miles per hour. And then for exploration missions, going to the moon, that's 25,000 miles per hour. So you can imagine the heat shield for that vehicle, for Orion, for example, is even more robust than SpaceX and Boeing because of the amount of energy required when that vehicle comes back into re-entry. And then, of course, the thing that Dr. Michaud and I concentrate on is keeping the human system alive in all of those missions. And there are a lot of changes that occur in microgravity. That loss of pressure against your bones can cause bone loss, and the calcium gets reabsorbed by your kidneys. That can increase risk for kidney stone. The fluid moves up into your thorax and into your head, and your head's not used to having a lot of fluid and pressure in it, and that can cause changes in vision and some changes in the brain. There are changes in the musculature that occur. Astronauts, when they first get to orbit, about 78% of them get a little nausea due to a change in the biofeedback when they are no longer walking on the ground and their eyes are no longer with the horizon. It can be a little nauseating for the brain until it gets used to that. So all of those things have to be taken into account in a mission, and all of the changes in physiology that occur over a 6-month period of time, if someone's on the ISS, for example, have to be taken into account. And then, of course, exploration missions even further. It takes 6 months just to get to Mars. Mars and Earth don't line up again for another 18 months, and then 6 months back. So that's a 2.5-year, almost 3-year mission. And so you have to take all of those things into account for a design reference mission. And we get involved even in the vehicle itself. When you think about a rocket itself, depending on whether you're using a solid fuel or liquid fuel, it can cause vibration and oscillation. And The solid fuels can cause even more vibration and oscillation than liquid fuels, and you can get what's called pogo. And pogo, think of a pogo stick bouncing up and down. When the fuel comes into the engine and fires out the bottom, it's thrusting the engine forward, but the rocket is getting lighter as it goes up into the air. And occasionally you can get pockets from the fuel where you get like a little burping of that fuel, or you have a little extra thrust upward. You can start to get oscillation up and down the vehicle itself, and that's called pogo. And you can start to get a vibration or a frequency when that happens frequently. And we have to make sure that it doesn't exceed the frequency for things like organs, the body's organs itself. And so looking at what hertz that vibration and oscillation of the vehicle has is actually important to know. Is that going to damage certain organs, or will the astronauts be able to see? Will they be able to perform their functions, to push a button, etc., due to the vibrations of those rockets? So we get involved with the engineers very frequently, just to look at all aspects of a vehicle and how it will impact the human system or the human factors. Now, we talked about the fluid moving up into the heart and brain and into the thorax. That can cause a change in vision for the astronauts. If you look at the eye down here on the left, the globe actually gets pushed forward, and so you can have flattening of the back of the eye. That's from the optic nerve pushing forward because of that fluid and that pressure. You can get what are called choroidal folds. If you look up here in the upper right, those are kind of, think of that like wrinkles in your carpet. You can get wrinkles in the back of the retina, and that's also from fluid and pressure. And that can change the vision for the astronauts. And we can have changes in the brain as well because of that change in the fluid and the pressure that occurs in the cranial vault. And those are things that we look at trying to make sure we account for in the human factors, but also look for ways to see if we can treat those entities. But it impacts the design. And if you can imagine an astronaut's vision changing 1.5 diopters from the time that they launched, this is the time that what they would see when they launched. You can read that switch 1, 2, 3, and 4 fairly easily. Here's a 1.5 or 2 diopter change. So that astronaut, being able to either fly multiple different prescriptions for an astronaut, or having it in such a way that we can change the font on dials or on glass panels. Those things are important as well, as you have that physiologic change and change to vision. And they can get what are called saccades. Saccades are this movement of the eyeball back and forth. And saccades occur when you have a mismatch of your neurovestibular system. And if you think about it, the astronauts are not walking on ground. They're not using their eyes and their semicircular canals in the same way that they would when they're on the ground. And you can get what's called horizontal nystagmus and saccades. And that saccade is the eyeball flipping back and forth a little bit when it tries to focus on something in particular. And so if you can imagine landing on Mars and you're trying to watch this dial for coming in on re-entry on Mars, and it's hard for your eye to stay focused on that. And that can cause obviously some problems on the human factors. And so that's why we would have things like artificial systems and AI to help support the astronaut when they are going to land on Mars, to account for any neurovestibular changes they might have. And can we give them maybe some feedback when they're on the treadmill to give them a visual stimulus? If you think about the AI goggles that folks have and virtual reality goggles now, could we use those for astronauts to give them some of that feedback that they're missing when they're on microgravity? But it does come into account. Even if you see the astronauts, it was a little hard for them to bounce on the moon, and we had a lot of folks falling as well. So neurovestibular issues are something we work a lot of. Radiation is probably the long pole in the tent, and that's one thing that we have to worry about on design reference missions. Even on orbital missions around the Earth, we have what's called the South Atlantic anomaly off the east coast of South America here, where there's increased radiation as the ISS passes through that ion belt. So we have to consider those things when we're doing spacewalks, and how many times we are in that area and what dosage the astronauts get. And of course, as they get further from Earth, they get exposures to more solar radiation as well as cosmic galactic radiation. And those can cause things like cancer or distortions to the DNA. So we worry about radiation and how to protect. And as Dr. Miller mentioned, we've looked at things from regolith to all sorts of different materials to see what we can do to protect the astronauts, whether they're on the moon, on Mars, or in a vehicle to and from those destinations. And then you have to take into account what kind of work they're going to be asked to do. And of course, the rovers are going to be much more robust than the rover we all remember from Apollo. But you also have to plan for worst case scenarios. What happens if the rover breaks down? Will the astronauts have enough oxygen in their suits to walk back to the habitat? Or do you have to put refilling stations for oxygen or CO2 scrubbing along the way to allow them to walk back and to hydrate on the way back if for some reason a rover would break down? So you have to think about those contingencies and the risks that are involved with all the things that they're going to be asked to do. And you have to think about things like lighting. Dr. Miller mentioned the craters and the potential for water in those craters on the moon. If you go to the south pole of the moon, the way the lighting occurs and tangentially there, it's pretty dark. And this is what in the lower right, what this looks like. We've actually simulated the angle of light and the amount of light that would have come across the lunar surface at the poles. And this is in the Neutral Buoyancy Lab at NASA at Johnson Space Center. So the astronauts have actually practiced what lighting they would have down in those craters as they look for water. And so those are things that you have to take into account when you're looking at these missions. Of course, medical care is one thing that we concentrate on as well. And how would we provide that medical care? Right now on the ISS, they have a flight surgeon that's on console and mission control that can give them instructions. But of course, the further you get away from Earth, the more autonomous they have to be, and the more they have to learn those different skills so that they can perform them on the moon or on Mars. And just simple things change for medical care. Eye drops don't drop in space. If you think about IV fluids and how gravity is used for those drops to drop into the fluid chamber, that doesn't occur either. And so you have to use things like pressure and other means of physics in order to accomplish the same thing, like intravenous fluids or putting medications into someone's eye. And we train the astronauts on lots of medical procedures like ultrasound. But even then, your patient has to be either strapped down or has to be holding onto a board. The astronaut themselves have a strap. As you can see, Chris here has a strap holding him down to perform that ultrasound. And then exploration care. What will we be expected to do on the planetary surface of the moon and Mars? And as Dr. Miller will probably talk about later today, the analogs are important. This is Devon Island on the left. This is up, close to the Arctic. And we do a lot of work at Devon Island to trial our different procedures and different equipment to see what would work on the surface, because the ground there at that crater close to Houghton Crater is very similar to what we would see on the moon or Mars. And so that's a good proving ground for us. And that's one of the reasons we're going to the moon in the first place, is the moon has 1/6G. A lot of the countermeasures that we're going to use on the moon, if they work in 1/6G, they should work in 1/3G of Mars. And so it's a good proving ground on the moon prior to going to Mars. Of course, countermeasures, whether that's exercise or other countermeasures, the longer you have humans stay on a surface, whether it's microgravity or if it's partial gravity on the moon and Mars, you got to make sure that they keep their bone and their muscle and the rest of their immune system and everything intact. And one of the best ways to do that, of course, is with food and nutrition, as well as countermeasures like exercise. And this is some of the exercise countermeasures on the ISS. That picture is actually not upside down. That's actually where the ARED, or the resistive exercise device, is located. You would think of it as being on the ceiling, but they can do squats. They can do all sorts of different resistive exercises there, deadlifts, and even bench press on that machine. The treadmill As you can see, the astronaut has to be anchored to the treadmill so they don't float off. It's also on a floating bag called a vibration isolation system. If you remember, we do very sensitive crystal experiments on the ISS, so you don't want to impart that vibration to the vehicle and disrupt those crystal experiments. So we have vibration isolation underneath that treadmill. So imagine running on a treadmill that you have to be anchored on, and the treadmill itself is on an airbag that's floating. And how difficult that might be, but the astronauts do a good job with that. And then SEVIS, which is an ergometer, which is on the side of the wall here, essentially like a bicycle where they can get a workout as well. But they do exercise 2 hours a day, resistive exercise for 1 hour a day, and the aerobic exercise for 1 hour a day. We worry about a lot of contingencies and how many G's someone can take, but also the survival of the astronaut, even if the vehicle fails. And that includes emergency aborts. If you watched Blue Origin last week, they did not have people on board. They had experiments on board their launch, but they had a failure of their rocket, and their emergency escape system deployed and carried the capsule away from the rocket successfully and landed back down in the desert. And so had people been on that Blue Origin flight, they would have done well. And that's what you want. You want a vehicle and a means for escape. This is the SpaceX vehicle with its thrusters coming off the side here, just above the trunk as it lifts off from a rocket. And then Orion, of course, has this launch escape tower, which has 4 rockets that help lift the capsule off from a rocket. And we have had astronauts need this abort. We had Nick Hague about 5 years ago on a Soyuz. He and his Russian counterpart, there were 2 crew members on that particular flight. And there was a problem with the rocket, with the Soyuz rocket, and fortunately had a successful abort and landed in the Kazakhstan desert unharmed. And that's what you want. And the vehicle designs and profiles give different considerations, right? If you're landing like a plane on a runway, that's a very different profile from a G standpoint, or different concerns and risks than if you're landing in the ocean like SpaceX, or on the desert floor like Blue Origin or Boeing. And there's Boeing landing in the desert with their airbags and their parachute as well. There's Virgin also landing like a plane. So very different profiles, despite the fact that they're both spacecraft, and different means of getting home, different ballistics, different Gs that the crew will endure. And so all those human factors come into play, and the design of the vehicles come into play. And part of our job as technical authorities, Dr. Michaud and I work very often with the engineering community and the safety community to make sure that they've taken into account all those things to keep the human system ultimately in good health, all the way from what vibration the engines give, all the way to how they land, and what food they eat and what exercise they do. So with that, let me turn it over to Vince, and I'll stop sharing here and see if there's any questions.
JD, there was a question you might want to address, but somebody mentioned with the increased risk of kidney stones, is it a less of a risk in space because of no effect of gravity on the organs, or does it change at all?
Yeah, it's meaning does it drop down through the bladder or not? And there's not a reduced risk in space. In fact, it's probably more of a risk because especially as we're on the ground, you have some element of gravity allowing that fluid to go into the bladder and continue draining. And you have to kind of push a little bit to get that fluid out against the detrusor muscle when you're on orbit. You don't have the assist of gravity. And so that calcium accumulating in the kidneys, and of course the difficulty and starting a stream without the assist of gravity can both increase your risk for that kidney stone. Good questions.
JD, there was another question about a Russian astronaut who was on board a space station for over a year. And the question is, how long did it take him to reacquaint himself to Earth And does he have long-lasting health conditions today?
Yeah, I'll answer that one kind of like an attorney, Ed. The word is it depends, and it depends on the organ system. What we see with the astronauts, if you've been up for a long time, 6 months or a year, it may take you 2 or 3 weeks before your neurovestibular system comes back to normal. In fact, we don't let the astronauts drive for several weeks after a long duration mission just for that reason. That feeling that you get like you're going to fall out of bed, that startled feeling, they get that often just standing still because they've had a dissociation between their neurovestibular system. Now, the bone itself, although we use bisphosphonates in exercise to retard bone loss, the bone itself can take up to 3 years from a 1-year mission until it has the same density and same strength that it did prior to flight. So a lot of it depends on the organ system. Usually the cardiac system responds the quickest. We give the astronauts IV fluids when they get back. We raise them up on the Starling curve from their cardiac physiologic standpoint. Within about 24 to 48 hours, they have the same ejection fraction that they had when they left. And a lot of that has to do with the exercise that we give them. But neurovestibular takes several weeks. Bone and the musculoskeletal system probably takes the longest to reaccrue and reacquire that calcium and that matrix in the structure for bone density.
All right. Thank you, JD. Are there additional questions for JD before we move on to our next speaker?
One of the things I'd like to mention related to the issue of standards and requirements that NASA sort of figured out about 10 years ago, but we realized that engineers make hardware based on requirements, and doctors are not usually versed in speaking requirements in the engineering sense. So we figured out that we sort of speak 2 different languages, and until you can deliver your recommendation, your health recommendation in the form of a engineering requirement, you're not as likely to get it to be done. So we had to work as an agency on the health side to speak like engineers to be more successful in getting those messages across in a way that would result in actual changes to hardware.
Very good. All right, Vincent. And with that, we will go ahead and transition over to your talk, the U.S. Space Force Human Support and Life Support Technology. Thank you.
Great. Thanks. It's a pleasure to be able to speak with you today. I will say that I'm going to speak a little bit less about the Space Force because I can't speak for them, but we'll talk in generalizations about what they might need and who else is asking those questions. But as was mentioned before, both JD and myself represent the Chief Health and Medical Officer's Office at NASA. And in that capacity, we both deliver policy and oversight of anything health and medical, which really spans a wide waterfront from occupational medicine all the way to taking care of the astronauts. And most importantly, to this discussion is helping the engineers build the hardware that we need to continue to explore space. So we do have a good experience base of putting people into space and helping them get to space and come back safely. NASA has over 60 years of experience, and that starts with assessing the risks and then trying to mitigate those risks and then help folks through the risks as they go to space. That experience base is important to a lot of different organizations. I've listed them here, but we have countries that have established space programs that want to exchange information with us. We have countries that are standing up new space programs, seems like almost on a daily basis. And they want to know about how to manage human space flight. And then recently we have commercial space efforts and private space efforts. And as mentioned in the title, of the talk, the Department of Defense has an interest in this, most recently with the standing up of the Space Force. So let me just sort of briefly discuss those various entities that are interested. But I mentioned countries are interested in learning more about the human health in space. And here's a list of the folks that have signed up to the Artemis Accords, which are a set of principles that NASA proposed to all countries who are interested in spacefaring or being involved in space flight. And these are the folks that have signed up so far. This is by no means an exhaustive list of folks that are interested in being in space or countries that have space programs, but you can see that people that want to sign up to a consistent set of ideas about it are actually pretty long already. I'll just mention a couple of the principles, and you can look up the rest of them online, but a couple of them that I think are interesting, and I'll touch on them a little bit, are interoperability and emergency assistance. So the intent is that if you're going to be part of the Artemis Accords group, that you'll strive for interoperability between your activities, your hardware, and anybody else's who's involved. And then also, if something doesn't go right for somebody and you have the capability or capacity to do it, that you will provide emergency assistance if able or if it makes sense. So those are extremely important concepts for the future. So I mentioned a few of the commercial entities that are out there and the private entities. As JD mentioned, there's folks that are doing suborbital flight like Blue Origin and Virgin Galactic. All of these entities that I'm mentioning are either involved with us directly or have talked to us for our experience on space flight and human health aspects of that, the standards before going to the space, and then the mitigations that we've come up with. SpaceX is providing us with both cargo and crew service up to the space station right now. They're also providing access to space for private entities. This is the first private crew that went to space, and they actually went to the International Space Station. They had an excellent flight, and they learned a whole lot for folks from that flight. One of the things that they realized, because they had scheduled a particular amount of time up on the space station and amount of work to do in that time, and then they were unable to leave on schedule. They had to wait a little bit longer for their departure because of weather on the ground, and they had almost double their mission time. They sort of ran out of things to do because they did it all in the first few days of their flight. The other interesting thing is that a different paradigm for us on the standard side, when we select folks, we usually select them for their physical capabilities, their ability to perform optimally in space. One of the standards that folks that operate in the private sector is that they can afford to go to space and they can afford to pay for it. So that enters into a new dynamic that we haven't had to deal with up until this point, I guess. But we're all going to get to deal with this as commercial and private space continues to flourish. As JD mentioned, we have our partner Boeing, who's going to provide crew flight up to the space station for us soon. And Sierra Space is working to provide cargo to the space station for us and hopefully crew as well at some point. And then I mentioned the DoD recently with the advent of the Space Force. They have now the opportunity to consider human space flight as part of their portfolio. Up until this point, they haven't done a lot of that. They've had a lot of programs over the years that were developed and designed for human space flight, but they didn't get to the point of actually operating. In the 60s, they had a couple of programs that went through design development and actually a selection of crews, but they didn't actually go to space with those missions. So now they've got that in their future, maybe in the near-term future, and they've come to us to ask a variety of questions. And that ranges from what kind of standards do you have both for your crews and for your hardware that that allow human spaceflight to be successful. And we provide those to the DoD the same as we do all those countries and private and commercial entities alike. Our intent is to give as much information to the enterprise across the front of space as we can possibly give out. And it's the same whether it's for our DoD partners or the other partners I mentioned. So I'll jump into a couple of technologies that have already been mentioned, but I'll mention them again. The first and probably the biggest risk for us is space radiation environment. This picture is really good in that it shows sort of visibly the impact of space radiation, and maybe more importantly, the protection we get from our magnetic field. As was mentioned before by both Dr. Miller and Dr. Polk, the radiation is out there. The magnetic field protects us from a big portion of that. All of the particular radiation goes around the magnetic field. So once we leave that magnetic field, we're exposed to the wide gambit that Dr. Miller mentioned early on. And the important thing about that is it's easy for us to think of radiation as sort of one threat, but in reality, it's a multitude of threats. It has a lot of different types of radiation, comes from many different directions, and has a wide variety of impacts to us physiologically. So currently on the space station, this is just a small representation of the radiation monitors we have to try and get an idea of what radiation is impacting the space station. And there's monitors here both inside the space station and outside the space station. There's many more as well, but they're only measuring what's in low Earth orbit, and therefore it's inside of that magnetic field. So we've got to spend time in our future missions, our exploration missions, trying to assess that radiation threat to the humans outside of that magnetic field. And we've started to scratch the surface with that with some monitors that we placed on the Mars rover. So we had some radiation monitoring as it transited from Earth to Mars and is now on the surface of Mars. But we probably need to do a lot more to understand what that environment really is outside of the magnetic field. Carbon dioxide has been a challenge since the beginning of any kind of closed space activities for humans. One of the notable places of this and where we got some of our first information was the submarine world. They are in an enclosed space for days and weeks at a time. So they had to come up with a way to get rid of carbon dioxide. We all give off carbon dioxide, and on Earth we have a small amount in the atmosphere. But if you don't take it out of a closed environment, it'll quickly build up to toxic levels. So the device in the picture here in the center of the picture that these two astronauts are working on is called the CEDRA, or the Carbon Dioxide Removal Assembly. And it removes the carbon dioxide from the air using a catalytic bed principle, which is very excellent. But that particular size device there is going to have to be shrunk down quite a bit to be able to be compatible with our exploration missions. Our capsules that might go to the moon or to Mars are not going to have the space or the weight ability to carry something that large. So they'll have to shrink that whole apparatus down to a smaller level. Similar to that, Dr. Polk already mentioned the exercise requirement to mitigate the bone and muscle loss. If I draw your attention to the pictures on the outside here, the left and right, the devices that are behind this in the wall are about the size of a refrigerator and weigh about the same as a refrigerator. The challenge here technologically is not to provide this capability because we've shown that it's very helpful and can mitigate the bone and muscle loss on the space station. But that kind of size and weight is not compatible for an exploration class mission. So we have to be able to deliver that same fitness capability for our crews going on extended missions in a much smaller size with a much reduced weight. So we'd like to shrink that capability down to something a little bit bigger than a shoebox. That's quite a challenge for our engineers, and they're working hard on that right now. Dr. Polk mentioned about the increased intracranial pressure and the visual changes that are resultant of that. And because of that, we have several modalities on orbit right now to look at the visual system and the eyes. I'll talk about the two at the bottom here in just a second, the OCT and the ultrasound. The pressure in the back of the eyes causes the eyes to flatten on the back and consequently make folds where the flat part appears on the back side of the eyeball. And that causes folds that we can actually see when we look into the back of the eye. And the upper picture there shows those folds on a picture. We'd like to know a little bit more about what the extent of those folds are. And so with a technology called optical coherence tomography, OCT, then we can look at the retinal layers, and those are the pictures on the bottom, with the normal retina layers being on the left and the post-flight on the right, and you can see the disruption of the layers as a result of those choroidal folds. I'm just going to jump back once real quick to show you that device again. So this device in the lower left-hand corner is that OCT device. And then one of the modalities that's been very helpful, not with just the assessment of the eyes, but many other assessments that we do on orbit, is the advent of the reduced size ultrasound. In this picture here, we show the Butterfly iQ, which is a handheld ultrasound. The entire device is in the wand itself, and you just plug it into your iPad to get the images from that. And that gives us a lot of imagery that we wouldn't otherwise have on orbit. It's not quite the same as having an MRI or a CT scan on orbit, but it does give us a great capability that we didn't have before. And we're learning every day how to utilize it more and more, and to try and get some comparable capability out of an ultrasound in the absence of those other modalities that would just be prohibitive to fly into space. And then on a non-health side, I mentioned interoperability before, but we've come up with the International Universal Docking Adapter, which you see in the lower right-hand corner here. And then there's a spaceship about to dock to that. That's going to be really important for all of the nations and all of the commercial entities to have the ability to operate together if we really want to push the envelope on the use of space. And I'll finish up my talk just to mention that it's not just the folks that go to space that we need to think about. We actually have people involved with the space program at all phases of space, both making the hardware and, in this case, the mission control, where they're operating the missions and the hardware in space. It's important to note that, like I said before, we do a lot of assessment and do health standards for our astronauts. But for NASA's purposes, we also have the need to assess our mission controllers, and we do physical standards for them and physical assessments on a periodic basis. You wouldn't want somebody to have a health problem while they're in the middle of controlling their aspect of the mission. This is something that's interesting to the Space Force. We mentioned before, they have a lot of similar needs as we do, but they have a large controller force as well on the ground. And one of the areas that they wanted to compare notes with us was about is how do we manage our health standards and health assessments for those ground crews. So I'll end my talk with that and see if there were any questions that came up.
Vincent, there's a question in the chat. Come back on the video here in the chat about would such magnetic countermeasures potentially disrupt communication and capabilities on the space vehicle?
Yeah, Ed, I think that one's talking about the magnetic field for radiation shielding for GCR. And the thing that we worry about with magnetic fields and what usually disrupts communications, radio communications, is the electrons. And so when you're coming screaming into the atmosphere, that's why we also with spacecraft have a blackout period when they first come through re-entry, and that's because of high energy electrons. When the spacecraft smacking into the atmosphere, you're literally ripping molecules apart and creating ionized oxygen and other elements, and that creates electrons around the spacecraft, and that's what causes the blackout period. But we can probably when we do GCR protection work around that.
Okay.
So I guess I would look at it a little, or look at the question a little bit differently. I think maybe the assumption is if we created a magnetic field to give ourselves that radiation protection like we have around the Earth, would we cause any effects for the humans inside? I think right now the answer is sustained long-term being magnetized for humans is probably not something we really know about, but it's probably something we would want to avoid. Certainly the hardware inside, you wouldn't want to have to operate in a magnetic field as well. The good news is technology is already there to be able to shape magnetic fields, so you could create a magnetic field around your habitat or your spaceship. But what we don't have is the ability to have the energy to run a magnet that powerful for that long and be able to sustain it. So until that technology can come on board, the magnetism is not really an issue, but it's something for us to think about as we go forward with maybe another mitigation for radiation in the future. Because even our shielding abilities with regolith or any other materials are limited, and it would be nice to have that same kind of shielding capability as we have with the magnetic field around the Earth, and they call that concept active magnetic shielding. So any other questions?
Yeah, there was a follow-up to that just popped up in the chat. And the question is fusion or fission, perhaps?
I'd say yes. We're looking at both. You're going to need nuclear type power when you're on exploration missions, and that electromagnetic field is very power costly. But that's one of the reasons to look at the moon, which Dr. Miller can probably speak to better than we can, is that the moon has an abundance of H3 in its soil, and H3 is a stable isotope of helium that is otherwise used in fission for nuclear reactions. And so that's another novel reason to go back to the moon, is to look to see if the helium-3 can be used for fission.
So nuclear propulsion and nuclear energy is very attractive for a lot of reasons, mainly the size and the weight and volume. Both of those are being actively looked at by many folks in the United States, both our military and ourselves and private entities, as a way to power. But you essentially create your own radiation risk by having those around our humans. And so you would have to create some sort of a way to shield against your own energy source in that circumstance. On a planet, you can use distance by just having a really long power cord off to your reactor. But if it's part of your engine for your rocket, then that's going to be a challenge for you in shielding against that. But both of those things, the bottom line is that chemical rocket engines right now is not a sustainable way for space explorations. They're hugely expensive, both in the cost of fuel and the weight. Right now, it takes about 1 pound, for each pound you take to orbit, it takes about 26 pounds of fuel. So that's not really sustainable with sending much weight anyplace. So there are a lot of different kinds of propulsion systems that are being looked at, and nuclear is one of those.
There's a question by Christian Hall, who is asking, space vehicles have to deal with atomic oxygen in low Earth orbit. Does this affect astronauts at all medically?
Not at the altitude and speed that they're flying at in the ISS. The atomic oxygen, where it comes into play, is on the reentry of the atmosphere, and that's when you think about the red glow coming off of a heat shield and the quote unquote plasma, a lot of that is atomic oxygen because we are literally cleaving or splitting those oxygen molecules when the aircraft or spacecraft comes in screaming at 17,500 miles an hour. So, nothing like Mach 18 to disrupt or create a wake in molecules and create that atomic oxygen. But it's a good question, and that we really don't have to worry about that too much at the altitude and speed at which the ISS is flying, though. But you do have to worry about it as a source for heat, especially when you're coming into the atmosphere.
So one area you might think about, though, with oxygen and atomic oxygen is in the area of radiation consequences. So as X-rays come into your cellular environment, they can strike things like water or oxygen in the cell and create a free radical. Again, that molecular oxygen, and that can be damaging to the cell the same way as it is to us in everyday life. Our bodies have repair mechanisms for that, and they do a good job. The question that we probably don't know the answer to is, do you get more free radicals when you're out in the space environment exposed to that radiation? And is oxidation a bigger problem to deal with for your cells when you're in that environment than it is here on Earth? So those free radicals can be a problem at your cellular level, but it's not from the outside environment that's causing it. It's what you're carrying with you.
Fascinating. This is cool. Really cool. Let's see. Any other questions for our panelist, for Vincent, JD, or Kristen? I will, while we're waiting for a possible question to pop up, another question to come up, the part 2 session of this talk will pick up at 2:25 p.m. and we will have 3 speakers, including myself. Arnold Nikosian will discuss space, human factors, and life support technology for exploration. And I should mention that here at the American Public University System, we are in the process of developing a space human factors concentration at the graduate level. It's being spearheaded by Arnold as well as Kristen Miller, and we hope to have this launched within the next year. Also, in the second session, starting up at 2:25, we'll have Francesca Schroeder, who will be addressing prospective space policies and legislations. And then I will talk a little bit about space habitat designs, including a new course we have here at APUS, an undergraduate course that we will be launching early next year, called Space Habitats, that ties right into it. And I'll say a little bit about our analog research missions at North Dakota, and also the Mars Desert Research Facility in Utah. But I will not steal Dr. Miller's thunder in the following session that I believe begins at 3:30, where she will focus on she'll have a panel discussion on the APUS analog research efforts. Okay, looks like Daniel has posted a question in the chat. Are the astronauts provided with medication to counteract potential side effects, I guess, of being in space long term?
Vince, you want to take that one? Well, I mean, I guess it depends on what which side effect you're looking for.
So for the most part, the answer is probably no. We do have some mitigations for space motion sickness, which is an acute symptom that you get right when you get to orbit. And it might limit your functioning for a couple of days if you didn't sort of mitigate it if you're having a bad case.
Vincent, how does that compare to being seasick, being out on a cruise ship and, you know, the meds that they give you to help with that? Is this, for our audience, is this totally different?
I think you feel just as miserable. First of all, I think the consequences are the same. I think the one thing that's different, JD can help me with this, is that the predictability is different. So if you were somebody who is susceptible to motion sickness on Earth, you may or may not be up in space. And then we've had some folks that are really not susceptible to motion sickness, like fighter pilots, who get up in space and they have those symptoms as well. And JD, you can help me with the medications are a little bit different than you use here on Earth.
Yeah, as Dr. Michaud mentioned, we used to call it space motion sickness, but that was a misnomer. It's really not due to motion. And we thought, oh, we'll just spin them around in a centrifuge or et cetera, and get them used to that, and then we won't have this. And that was actually not helpful. It's really has to do with the feedback to your brain. If you think about it, when you're on a bicycle or if you're walking down a sidewalk, there's about 1,000 different signals that your brain gets at one time. Your eyes with the horizon, your semicircular canals saying whether your head's forward or backward, the stretch on your Golgi tendon apparatus of your tendons telling you whether you're extended or flexed, the pressure on the balls of your feet, all of those simultaneously telling you where you are in space and time. And then you get to space and suddenly in an instant, all of those are gone. The guy next to you is upside down, so your eyes are lying to you. Your otoliths are floating in the semicircular canals. There is no pressure on the balls of your feet. You're slightly flexed. There's no stretch on your Golgi tendon apparatus. And so you've got about 6, 7, 8 things that I can think of and rattle off. There's probably 100 that your brain is used to getting that signal, and all of a sudden it's the opposite or different than what it's perceiving or looking for. And sometimes your brain, when it gets an anomalous signal or multiple anomalous signals, says, I don't know what's going on, but I'm going to throw up. You think about it, you have that in other things, right? When you're having a heart attack, you often hear about people having nausea with a heart attack. Well, it's not because your heart is somehow wired, to your gut. It's because of, that pain going up to your brain and excitement of the vagus nerve and other things to where your brain says, all right, this is really anomalous. I'm going to throw up. And that it happens with head trauma. It happens with kidney stones. Nausea very often occurs as a biofeedback from your brain when it gets a lot of anomalous signals. And the medications we've used, we still use a very old medication called Phenergan, despite the fact, I always have comrades and colleagues say, hey, what about this new medication that we use for chemo or this, that, and another? The advantage to Phenergan is it's cleared through the liver and it has what's called first pass phenomenon. So when we give it intramuscularly to an astronaut, it has a very fast onset to get rid of the nausea, but it has a very fast offset because of the fluid shift. It's one of the few medications where that fluid shift and moving things up to the liver and increasing that first pass is actually beneficial because it has a quick onset and quick offset. And once the astronauts get past that initial nausea and their brain gets used to, okay, I got it. This is what spaceflight is. Then they get past that.
How do we, let me ask you this question. I often have students who are interested in becoming astronauts, but fear, and I'm sure this is something that you have addressed on many occasions, have fear of being in a spacesuit and becoming nauseous and throwing up. How is that handled, and how often has that happened during an EVA? I'm sure it's embarrassing for the astronaut, but it's certainly something that can and probably has happened quite often.
Actually, it hasn't happened. And the reason for that is we schedule the EVAs after when we know the space motion sickness or the space adaptation syndrome that we call it now is over. So you never see somebody do a spacewalk, immediately after they get to space. And that is just for that reasons, because about 70% of them are slightly nauseated. So we treat them, but within 24, 48 hours, they're good. So their spacewalk could be scheduled after that. The bigger danger that we've had is, as Vince can talk about too, is we have cooling in the spacesuit because of, as Kristen mentioned, changes in temperature between light and dark. You can get about a 300 to 400 degree change in a spacesuit, and so we have liquid cooling. And we've because of the age of the spacesuits, they're getting up there. They're pretty ancient. They're kind of like the B-52. We just keep recycling them. They have developed a leak, and in one with Luca Parmitano, we had a leak in the helmet. And he was in danger of drowning in space and aspirating that fluid. And that's been our biggest risk, is aspiration when we have anomalous fluid in a helmet.
I know we're just about out of time. We're going to wrap up here in about 4 minutes. And yeah,
Ed, can we just finish on the medication side?
Yeah, go ahead, Vincent.
JD really touched on it, that it's easy to think of medications as countermeasures, and you can think of a lot of countermeasures for the things you might think about as far as things in space that you want to try and combat. But you got to have that physiology behind it of the medication in the environment, that you need to really think about it. Several of our medications that might mitigate some of the challenges we mentioned today change your acid base curve. And if you do that in space, you're going to increase your kidney stone formation by leaching more of your calcium. So we have to really look carefully at mitigation medications before we allow them to be used. So that's why we don't routinely use them for a lot of different things, because there are those secondary consequences that either you have to really think about ahead of time, or you just might not know about it till you have them in space.
All right, thank you, Vincent. And just on a final note, JD, since you brought it up, the spacesuits, and this is always have been it's of interest to me and my students. Having grown up during the Apollo era, I was always fascinated with the technology of the spacesuit and how it was really almost a showstopper for the Apollo missions, not having the spacesuit ready in time. And it's interesting how we're kind of back in that mode with Artemis, trying to have human boot prints back on the moon. And the issue now is the complexity of the new lunar suit. Can you speak to that at all, and how that might be coming along, keeping in mind that we only have about 2 or 3 minutes left?
Yeah, I'll see what I can say, because we have it out for solicitation and I'm on that committee. So I'm in blackout for what I can talk about to some degree. But, one of the things that we were trying to do, whereas before it was down selecting to a single vendor to work with the government. Now, as we go to the moon, it's different than when we went in the 60s. We're going with our international partners. We're going with multiple commercial and private vendors together as a large team. And with that, you get the innovation of multiple different companies, right? And so, although they have a company that was down selected recently onto the prime suit, each of the vendors have come up with different ideas for their suits for their lander or their module and things of that nature. And we've put a lot of funding into the academic aspects at different universities. North Dakota, I know, is working on one, but also other countries. Iceland has a pretty cool looking hard upper torso suit and have tested it on glaciers, which is, they're pretty radical. But I think that's the excitement that we have is on when we return to the moon this time, Ed. It's not just the United States going. It's I think more representation from all of Earth going as humanity, because we've got a lot of international partners, as Vince showed on the Artemis Accords. We've got commercial and private entities going. It's we're looking at not just going to the moon to say we've been there. We're looking to go and use it as a proving ground to go to Mars, and then beyond that to expand humanity to where humanity is no longer a single planetary species, that we might be across a couple of different planets. And that's, it's looking at a lot of these things with new eyes.
How exciting. Thanks so much, JD. This is really cool. And some interesting insights into the workings of producing the new spacesuit. All right, folks, we're at the end of our time. Thanks so much for the great questions. And thank you so much to our great three speakers. If you enjoyed this presentation, I wanted to remind you that we'll have part 2, which will occur in room 1 of space, human factors, and life support technology for exploration. So that will pick up at 2:25 p.m. Otherwise, have a great afternoon, and thank you so much for attending and your input this afternoon.